I want you to believe that knowing about weak acids and about the Ka values of weak acids is a worthwhile use of your brain cells. These numbers are incredibly important in biochemistry, and understanding how weak acids can make interesting things and incredibly important things happen in biochemistry hopefully will help you make the effort to sort of get to grips with what's going on with them. So I just wanted to talk about the mechanism of action of a class of enzymes which are called Aspartic Proteases. There are lots of enzymes like this which all work in basically the same way. They're not particularly closely related structurally, but they sort of converged often on this same kind of mechanism. So for example, pepsin in your stomach works like this. Cathepsin, which is an enzyme that you have in your lysosomes, which are the little compartments in your cells in which things get broken down, that, you know, foreign material in the cells or waste material in the cells get broken down, works in the same way. And perhaps most famously in recent years, the Hiv protease, which is a key enzyme that plays a role in the life cycle of the HIV virus, is an aspartic protease. And understanding how that enzyme worked was the key to designing one of the major drugs that keeps HIV positive people from developing full-blown AIDS. So that was a really important piece of enzymology that led to that. So they're all proteases, which means that they chop proteins up into fragments. So if we think about that reaction, it's hydrolysis of an amide, right? So it's a reaction you know about. So if we think about a polyamide in general, you know, the idea is that you have that as your, no, let's do that again, sorry. So a polyamide repeat unit, remember, has this as its basic structure, where you have an NH and a CO group forming the linkers, so that you end up with this NHCO secondary amide group, which in biology is called a peptide link when it's linking amino acids. So because we are talking about proteins, this group X in the middle is basically this, where you have CH and then a side chain which we'll call R, and that's the thing that varies between the different amino acids. So that's the basic structure of an amide, a polyamide thing. And remember, what happens in hydrolysis is that you would react that with N-1 waters, and that would give you N lots of the original amino acids, which will look like this. Okay, so that's the reaction which is catalyzed by the aspartic proteases, and it has to be catalyzed because the rate of that reaction ordinarily is extraordinarily slow. That has to be the case for life to work, because obviously if your proteins that you're made up out of reacted easily with water and broke back down into their amino acids, life would be completely unstable, because the proteins you're made out of would constantly be, you know, dissolving in the water in your body, and when you went out for a walk in the rain you'd dissolve and form a puddle on the pavement. So it's really important for life that this reaction has an incredibly high activation energy, so the rate of it under normal conditions is extremely slow, but it can be catalyzed, and if you have a suitable catalyst you can make it happen at a reasonable rate. So in order to understand how the aspartic proteases work, the first thing we should do is look at why water finds it so difficult to make this reaction happen, and in order to do that we need to think about what the mechanism is. Okay, so there's our amide link. So this would be part of the long protein chain, but what we're aiming to do is to just break that link open so that we're breaking the protein into bits. So if we have just water, no catalyst to start with, here's our water molecule. And if you think about what you know about reaction mechanisms, obviously we haven't studied the mechanism of hydrolysis, but we have studied the mechanism by which carbonyl groups react in other contexts. In the case of aldehydes and ketones, remember, you need to know about the nucleophilic addition mechanism. And the key to that, remember, is that this is a very polar bond. So that delta positive carbon is going to be very attractive to nucleophiles, to something with a bit of negative charge or a partial negative charge and a lone pair of electrons to home in on it. And of course water has those things, because water is quite polar, and in particular one of those lone pairs of electrons can mount an attack on the carbon atom like that. And as usual, because carbon can't have 5 bonds, if it's going to accept that incoming pair, it has to boot out a pair, so the pi bond will break because that's the weakest one, and we'll get that. So if we look at the consequence of that, let's just draw what happens next. So we've got this. So up here, that's easy to see what's gone on, because the oxygen is now only singly bonded because the pi bond is broken, and because that pair of electrons has moved and become a lone pair on the oxygen, we should show that. And of course, in effect, that means that oxygen has one more electron than it had originally, because it used to be sharing this pair, and now it has it all to itself, so that becomes O-. Okay, so what about what's going on down here, where the water has attacked? So we know that we've formed a new bond to the water, so the lone pair there has become this bonded pair here. But that can't be quite right, because you can see by looking at it that the charges don't balance. Overall, everything adds up to 0 charge on the left, and so that must be true on the right as well, and it doesn't at the moment because we've got a negative charge here. And of course the reason is because this oxygen used to have this pair of electrons to itself, but now it's sharing it, so that oxygen has become positively charged in order to make that intermediate. So what we're saying is that that process of getting to there has a really high activation energy. After that, it's relatively easy to complete the mechanism. We'll just quickly look at what happens, but this is the step we're going to be concentrating on, actually, because this is the high activation energy step. Once you get to that, it's quite easy to do the rest. So what happens, first of all, or at least the timing, I'm not sure is that well known, or certainly not to me, but essentially what happens is that one of these protons gets grabbed by the nitrogen. So in effect, I suppose if we wanted to draw it as a curly arrow, it would go like that. Okay, so the nitrogen is able to grab a hydrogen from the water, and the effect of that is that you now have an extra hydrogen attached here, and that nitrogen has the positive charge. The oxygen has got its lone pair back, and so it goes to a neutral thing. So that's the first step, and then this comes back down here to recreate the pi bond. Again, a bond has to break, and the one that's going to break is this, because the effect of that, if we just draw it out, is that we get COOH and we have NH2. Okay, so you can see marvellously that what we have done is to break open the peptide bond. So we've got a separate chain here and here. And that's the essential mechanism of the reaction with water, except that it doesn't happen because the activation energy is so high. So what we have to ask is why the activation energy is so high. And the answer is that neither of these oxygens is really very happy in that state. You know that an O- ion like that doesn't form very easily, because remember the story about alcohols is that when you think about the acidity of alcohols, okay, which is that reaction, what you've learnt this year is that the equilibrium for that lies far over to the left. Alcohols effectively are not acidic because that equilibrium lies so far over to the left. And we rationalise that by saying that this negative ion has a high energy, and we compared that, remember, with a phenol, which was more acidic because in the negative ion you can delocalise that negative charge. Okay, because the negative charge can be spread out around the ring in effect because of the lone pair on here becoming part of the delocalised system. So in other words, what we're saying is that when you have nothing to stabilise a negative charge, even something that's very good at attracting electrons like oxygen really doesn't cope very well with it, and so that makes it a high energy state. This one, again, oxygen's very electronegative. It's going to attract its pairs of electrons very strongly, and so it's really not particularly favourable for it to be sharing there. So neither of these oxygens is in a very favourable low energy state when that intermediate is formed, and so the combination of both of them raises the activation energy up through the roof. So if we're going to catalyse this reaction, we need to do something about one or other or even both of those charges. And if we can do that, we can lower the activation energy. Now, before we get on to how the enzymes do it, it's just worth saying that there are simpler catalysts which can make protein hydrolysis much faster. And an obvious one is alkali. So for example, that you can unblock drains with concentrated alkali, and that's because they're very good catalysts for hydrolysis reactions. And you've learnt the mechanism indeed or rather not the mechanism, but the equation for hydrolysis of esters and amides catalysed by OH-. So let's look at how that could work. And you can see, so if we just get rid of these curly arrows for the moment and then just modify this scheme slightly to show how it would work in the presence of an alkali. So if we have OH- here, you can see that what can happen is that can grab this proton here, and what that means is that instead of having to use a lone pair to attack the carbon, which is going to make the oxygen positively charged, it can in effect use that bonded pair. And that makes a huge difference because the oxygen won't become positively charged. It's just swapping one bond to hydrogen and replacing it with a bond to carbon instead. So it's not very different. That is going to make a dramatic difference to the activation energy. What goes on up here is the same. So what happens then is that your intermediate just looks like this because the proton has gone. It's been grabbed by the OH- and you have water down here. This is still O-, and you can see the charges do balance here because you had OH- there and O- there. So that shows you how an alkali can lower the activation energy. You probably also remember from the organic chemistry that we've done that acid can catalyse the reaction. And again, we can have a look at how that happens. So let's get rid of our curly arrows again, and then think about what can happen if we've got H+ around. So let's just put the H+ up there. So we can mount the attack like that, like we did before. So that's not going to help us at this end because that's going to be the same story as before, but it makes a difference here because when that bond breaks, instead of forming a lone pair on here, which we've said the oxygen doesn't cope that well with, it can do this. And the consequence of that is that you get this going on down here, same as it was in our original mechanism, but up there, instead of getting the oxyanion like that, you get OH. And that's what our intermediate looks like now. And again, it's not as bad. We've still got this, which isn't great, but we haven't anymore got the O- up here. And so that again will lower the activation energy. So that's why both alkali and acid are capable of catalysing hydrolysis of amides and indeed esters in much the same way. So now finally let's get on to how the biology does it. And as you know, if you've looked at any sort of biological applications of chemistry, biology just does it better generally. So we as chemists have sort of said either you catalyse it with acid or you catalyse it with alkali. Because obviously if you're doing this in a bucket or something, you can't have both there. You can't have acid and alkali at the same time because they would react with each other and effectively wipe each other out. But biology, of course, is clever. Because it's doing it in the active site of an enzyme, what biology is able to do is to have acid catalysis and base catalysis happening at the same time. And the combined effect of both is hugely better than having just one or the other. So let's then have a look at how this happens in an active site. So the clue here is in the name of the enzymes, aspartic proteases. Now what aspartic refers to is aspartic acid, which is an amino acid that looks like this. Okay, so this is the R group of the amino acid, is CH2COOH. These groups, remember, which are in the amino acid, when it's part of a protein, these become swallowed up into peptide bonds. So it's that group, the side chain COOH group, which remains as an available weak acid group, and that's the key to the mechanism. So what happens is that if we draw the bits of the protein in pink to distinguish them, that up here you have one of these aspartic acid groups, which is attached to a protein. So let's just draw this and say, right, this is the active site, but it's got this aspartic acid group. And it will be, remember, this won't just be sort of floating around with a rough, vague chance that it might bang into that one. The whole point about active sites is that the substrate, this protein molecule, gets locked in place so that this will be in exactly the right place to interact with that aspartic acid when the mechanism kicks in. Meanwhile, over on the other side, down here, you have another aspartic acid group, but the key difference is that this one is ionized. So instead of being an aspartic acid, it's an aspartate group, which means that it looks like this. And we'll talk about how it's possible for this one to be not ionized and this one to be ionized in a bit, but for the moment just accept that that's the way it has to be for this mechanism to work. Okay, so these are both the same type of amino acid, and in fact in some of these proteases, in the Hiv protease for example, the way the enzyme is made is that you have two protein chains identical to each other which come together, and the active site is formed at the interface, and these two aspartic acid groups are actually the same group. You know, in other words, it's residue 211 or whatever it is in each of the chains. But when you assemble the active site, it turns out that one of them is protonated and the other isn't. So how's this going to work? Well, you can see it's actually not very difficult once we've understood the way that H plus and OH minus worked to put together a mechanism for this, because what's going to happen is that you can use that lone pair to pick up a proton from the oxygen, the same way that OH minus did it, and that enables that electron pair to be used to attack the carbonyl group. So we're doing the same thing OH minus did and avoiding this oxygen becoming positively charged. Meanwhile, this pi bond breaks, but instead of going out onto here to form an O minus, it's used to pick up the proton there. And in fact, if we just redraw that slightly to show the bond, that'd be better. Okay, so we've got OH there, and this is going to, this electron pair is going to be picked up by the hydrogen here, and you do that. Okay, so then what happens? Well, if we draw out the consequences of all of that over here, that's where we get to. So you can see that now the intermediate that we formed has neither the positive charge that we originally had there nor the negative charge that we originally had there. It doesn't have any of that. We've avoided that by bringing these two catalytic aspartate groups into play. So that's our intermediate, and then we can complete the reaction in a very similar way to the way we did before. So if we transfer H plus across to there, we get this, and then we can do this and that to complete the reaction. So that will, if you follow those curly arrows, you can see what's going to happen is that you get C double bond O there, this bond is broken, and you get NH2 there. And these are the two products which, because they're now separate from each other, can just fall out of the active site. So we've done what we needed to do. We've clipped the chain so that we've broken the protein into fragments. So those fragments can then escape from the active site. And the final thing that has to happen to return the enzyme to its original state is that this H plus has to jump back across to there to return the enzyme to its original state, so that you get OH up here and O minus down there. And now we're good to go again. So we can follow exactly the same mechanism as we had before. So that's essentially how aspartic proteases work. And the key feature, the reason I'm talking about it in relation to weak acids and so on, is that these two weak acid groups were the key to it. Without that, it wouldn't have worked. And the thing that's weird is that one is deprotonated in the conjugate base form, the other one is protonated. So how is that possible? Well, the answer is that actually these two are very close to each other in the structure. So, you know, we've sort of spread it all out like this, but remember, actually these things are all going to be jammed close together in the active site. And so if they were both in the deprotonated form, you would get strong repulsion between them. Right, so if you had these two negative charges here, in reality they're very close in space, and the strong repulsion between them would raise the energy. And so that's why it's favourable for one of them to be deprotonated but not the other. That doesn't explain why the proton should be specifically on one rather than the other. And the answer to that probably lies in the asymmetry of the active site. If you have the Hiv proteases, as I say, you have two equivalent chains packing together to form the active site. But once you put a substrate in there, that breaks the symmetry. And it means that the environment that this one sees is different from the environment that that one sees. And that's probably why you find the proton on this one, to leave it in the neutral form, and this one being deprotonated. Now, how does all that relate to Ka? If you think about this number Ka, which we've learnt about, Ka is equal to H plus times A minus, so I'm not going to write out the whole aspartate structure, so we'll just call it A, but A minus over HA. So that would be our Ka for an aspartic acid residue. And if you just rearrange that a little bit and move the H plus over to that side, remember it's going to slide diagonally down there, you get that Ka over H plus is equal to A minus over HA. So that's a very interesting expression, because what it tells you is that the ratio of how much deprotonated what it tells you is that the ratio of how much deprotonated aspartate relative to the amount of protonated aspartic acid just depends on the ratio of Ka to the proton concentration. And of course that's consistent with Le Chatelier, right? If we just think about that, we're talking about this equilibrium, H plus going to H plus plus A minus. And Le Chatelier tells you if you increase the proton concentration, this equilibrium is going to shift to the left to oppose the change. So you're going to get more HA and less A minus. And that's what this expression says, right? If we increase the H plus concentration, this ratio is going to get smaller, so that ratio has to get smaller. More H plus, more HA, less A minus. So this is a really useful expression, and what's even more useful is to think about it in terms of sort of 50%. If 50% of the aspartic acid residues are ionized, those two concentrations will be equal, so the right hand side will be equal to 1. And therefore this side must be equal to 1. So in other words, we can write down that when 50% is ionized, Ka is equal to H plus. And you're also used to pKa. Remember, pKa is equal to minus log of Ka. Just the same as pH is minus log of H plus. So we can rewrite that in terms of pKa and say that when it's 50% ionized, the pKa is equal to the pH. And that's why biochemists love this number pKa, because it means that if you know the pKa for any particular weak acid group that's important in the chemistry that you're looking at, and you know what the pH is in the compartment of the cell or wherever the enzyme is doing its stuff, then you can tell whether that weak acid group is going to be mainly protonated or deprotonated. Okay, because if your pH is lower than the pKa, it means it's going to be mainly in the protonated form, right? Because if H plus is higher than Ka, this number will be less than 1, which means you're going to be mostly in the HA form. On the other hand, if the pH is higher than the pKa, that means H plus is less than Ka. It means that, yes, H plus is less than Ka, so this number will be bigger than 1, which means it will mostly be in the deprotonated form. Okay, so this expression, and in particular in the pKa form, is the key. So, if you draw a graph of the enzyme activity, so the sort of rate of reaction in the presence of the enzyme as a function of pH, what you get for one of these aspartic proteases is a curve that looks sort of like this. And you can see why that is, why there is this optimum range in which the enzyme works well, but if the pH is too low or too high, it doesn't work well. Because what you have are two different pKa values for these two aspartates. Because remember, what we needed was one of them in the OH form and one of them in the O minus form, in order to do that trick that we saw. So what we need is for the pH to be below the pKa for this one. Okay, so for this one to work, we need the pH to be below the pKa, so that it will primarily be in the protonated form. But for this one, we want the pH to be above the pKa. So in order for these two things to coexist, this one protonated, this one not protonated, they have to have quite different pKa values. And so long as you're within that pH range where both of these conditions are met, which is in the middle somewhere, then you can have that, because the asymmetry that you get when the substrate is bound allows it to be more favourable for this one to deprotonate than that one. But if the pH is too low, what will happen is that both of them will be in the protonated groups. Okay, so if both of them, the pH is below the pKa, you get that. And then the enzyme activity, it's not necessarily completely abolished, but one half of the mechanism, you know, the bit that depends on base catalysis is not going to work. So the enzyme's going to have impaired activity. On the other hand, if you go to this part where the pH is too high, then the pH may be above the pKa of both of them, and then they'll both be in the deprotonated state, and that means the acid catalysis, the bit where we donated an H+ to take away the negative charge on the intermediate, that bit's not going to work. So again, we lose a big chunk of the enzyme activity. And in fact, lots of enzymes, although the details of the mechanisms may be wildly different from this, but many, maybe most enzymes sort of optimize the charge distribution in the active site as the reaction progresses by moving protons around in exactly the kind of way that we've seen here. So that's why lots of enzymes are very dependent on pH, because if the pH is wrong relative to the pKa for any of those key residues, so that they haven't got a proton to donate when they need to, or they have got one already and so can't pick up another one when they need to, then the enzyme's not going to work as well. And that can make dramatic differences to the activity, you know, many orders of magnitude difference in the rates of reaction that can be obtained. So biochemists really care about pKa values, and that's why.